Hello friends, welcome to Mechanism Group. Here we'll discuss about different engineering topics which will be helpful for professional career. Coming to today's topic, we'll discuss on tolerance stack-up analysis. This is Anil Kumar. We'll move on to next. Introduction. Tolerance or a tolerance stack-up is a variation on a assembly, on a part, or on a drawing. If you accumulate those things, then it is called as tolerance stack-up analysis. This tolerance stack-up analysis will be done by looping mechanism. The design of the parts and dimensioning of the drawings. Based on this, we will do this one. Tolerance loop should be completed for all critical gaps, alignments of the part, and clearances, which defines really how much tolerance we need to give for a part. Coming to what is tolerance stack-up analysis mean? As a definition, we'll just go. Tolerance stack-up analysis is a mathematical calculation used to measure the gap and interference value between the parts in an assembly due to variation in the form, orientation, and location. And one more definition also, like tolerance stack-up analysis is an analytical reasoning tool used to decide the allowable value of interference gap between parts from the key perspective of its functional requirement in an assembly and its manufacturability. Finally, from tolerance stack-up analysis, we can find how much interference a part can have, how much gap a assembly can have. This will give say whether it is a good part or a bad part. Why tolerance stack-up analysis? To ensure that all the parts fit together in assembly, and another one to ensure that allowable values in the form due to the variation in the manufacturing. Another, to understand the worst case fit and form of all parts in an assembly. To manufacture the parts by assuring the allowable variation in the size and location. Next, when should we use tolerance stack-up analysis? At the design stage before drawing release. And coming to next, how many ways of tolerance stack-up analysis? Stack-up analysis we are having. Linear stack-up, radial stack-up, part and assembly stack-up. What are the advantages of tolerance stack-up analysis? Thorough understanding of a functional requirement of each and every part in an assembly. Prevention of quality defects and improved product quality at design stage itself. Cost reduction due to the optimized tolerance. Reduction in development time to market. Improves customer satisfaction. Before going to manufacture itself, we are analyzing how a assembly will act when all parts are put together. What are the problems may get? So these all things we can get by tolerance stack up analysis. Four basic steps of a tolerance stack up analysis. We should have a clear definition of a problem. Define whether where do you want gap interference in an assembly. We should know where we are trying to figure out a gap. Second one, select the acceptance criteria. What is the desired answer or result in a gap interference one? Because for some parts they need a precision manufacturing, for some parts they need no need of precision manufacturing. So whatever our acceptance, based on that we can decide. Third one is identify the stack path in an assembly. What all features of size or features that impacts the variation. Whatever gap we are trying to figure it out, we need to stack all the parts, and we need to see what are the variations might happen after manufacturing. Perform mathematical calculation. Here we'll make some assumptions in stack. Variations in microns due to following factors not considered in stack up analysis. Parts are at room temperature. Parts to be print and drawing. No wear, no zero deflection, no unusual conditions. Problem definition. Clear definition of the problem. Document the stack object, list the condition under which stack is being calculated, label the start point, end point, and direction of the stack. Rule for starting point. Axial stack starts on the left, radial stack starts on the bottom. Stack indicator example. Start point, a feature. These are the basic definitions which we need to understand. Like start point, a feature is a surface of a shoulder, the first part in the stack. End point, a feature is a surface of groove surface, second part in the stack. Stack objective, find the maximum and minimum distance between the shoulder and the left side of the groove. Stack indicator, the positive and negative directions for the stack. Here in the diagram we can see stack indicator here and stack objective. This is one. Identify the stack path. What is a stack path? A series of chain of distance from start point to end point. This chain consists of only known dimensions. To identify the stack path, locate the shortest continuous chain of distance or a path dimensions, derived dimensions. Make each dimension with a line, place a dot at the starting point and arrow at its end. Label each distance with a letter. That's where we'll have a clear idea how we are traveling from start to the end, in what direction, whether it is plus or minus. Here we'll have a pictorial information of it. See, here we are finding x value here. This x value will be derived from these all imperfections, means tolerance whatever we have here, based on the directions. If we see top side, uh, alphabet D, A, B are in different direction and C is in different direction. So we need to consider one thing, like towards uh, left those things are minus and towards right is plus. Finally it gives a value, and we need to add the tolerance of these things in the same fashion how we took. Here we need to add all these things plus or minus, which gives the tolerance value. And there are some basic rules should be followed for loops. Every dimension in the loop must be on a drawing. Use real capability data. Don't assume the data or the drawing for current parts are accurate. Don't rely on process capability improvements to make a loop meet requirement. Discuss the loop with others. This is very important point, because which makes our path or the calculation of tolerance stack-up analysis will depend over here. Like review with others as a checkpoint or checkpoints can help you. Validate the loop response, assemble the parts and measure the response. Put the actual dimensions and characteristics of the part assemble in the loop, compare the response to the measurement. Update the loops when tool parts are in hand. Store the loops where people can find them in future. Problems due to tolerance stack up includes failure to assemble. If we won't do when it is getting assembled in the part, it may fit, may not fit. If we don't know statistically whether it is a good part or bad part. Interference between the parts, failure of the parts to engage, failure to the function as intended. Here, as a regular practice, most of the time we will follow worst case analysis and standard deviation method. So worst case analysis, we will just method to establish the extreme limits of y. Assume that all x can be at their extreme limits simultaneously. Guarantees 100% interchangeability. Imposes very stringent tolerance on x. Worst case analysis for linear transfer function. These are the formulas which we need to use. In coming slides, I will just, so here we'll just make some brief way how we'll make. Block must not interfere with envelope. This is a very simple example where you can understand how it is here. The first one, the picture over here which I am trying to highlight here, this is an assembly where one envelope is there, four blocks are there. Here our problem statement is very much clear. We are trying to find the gap, the y gap. This gap we are trying to find. So after that, what we did, in which direction we are trying to make, we made. Like if it is from left, towards left it will be minus, towards right it will be plus. So from block to block we are having one direction which is will be in negative, and one left to right it is there, it will be in positive. So in other figure, third figure, we can see that one like minus 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 like this it went, and here it is plus. So blocks, so if we make some like rough dimensions, like blocks will be 1.24 plus or minus 003, and envelope will be like this one. So gap will be 0.125 plus or minus 0.125. So how we'll get that one? By block 4 minus block 3 minus block 2 minus and adding this one x envelope. By calculating over here, we'll get this value, gap value. So whatever I have explained here, it is like step by step, like identify the gap, means why, generate a layout sketch, how it travels from left to right, right to left and left to right. Based on this, our symbols will change, like whether it is positive or negative. Create the vector loop, assign the sign functions to the vectors. Steps: perform tolerance analysis, like whatever we y is equal to x block, if we make this one, we'll get y value this one. In the same way, tolerance y, if we consider tolerances of the block for this all things, by adding these all things we'll get 0.15. Worst case limit, here we'll find like maximum and minimum. Maximum y nominal plus tolerance y, means if we take this one and this one, if we make plus value, this one will be the 0.0275 will be the maximum gap it can accommodate, and bottom one is the minimum gap which will might occur. So here one more example where we can see, if we are going upside here, it will be plus. If we are coming from top to bottom, then it will be minus. And here the problem statement is clear. We are trying to find this gap. So firstly we need to make these vectors, as it is going top side it should be plus. From there it need to link all the parts. Here if you see, everything is touching from this one to this one, this one to this one, this one from top, from here it is touching this one, from here to here. So by adding these values and removing from this values to this value, we'll get a gap value over here. Here the same thing, it solution which we kept on a Excel sheet. Earlier I have shown a worst case example. Here it is a like a standard deviation method. Based on that, how much uh, we'll get. Bottom, if we see, one is by worst case method we got, and another one is by RSS method we got. So here just screw length, we need to make the mean value and its tolerance, and washer and its tolerance, PCB thickness and its tolerance, frame thickness and its tolerance. Like this, we need to figure out all the things, whether it is plus and minus, what value also we need to give. Accordingly, we'll get a one value that will be y gap and tolerance of it. And if in minimum side, If we remove from 0.74 to this one, we'll get a minimum value, and if we add, we'll get a maximum value, which will be the thumb rule how much a part can vary. So in the same fashion, if we root mean square, if we do, we'll get these tolerances, and these are the things. From this, if we make the same combination plus or minus this combination, we'll get this value. 0.005 will be our minimum value, and 0.05 will be our maximum value. So this is the main fundamental. Other two case studies are there. Just you can implement to this one and test your things, one and two. Thank you, friends. Let me know any suggestions and improvements. Just this is my experience and learnings, whatever I have. Thank you.